Okay, let me get started. Wait, not there we go. Okay, um, I'm Alan. If you don't know me, I'm Alan Cash. I live in Barcelona. I'm these days I'm a freelancer working mostly for the University of Ghent, and I'm doing a lot of work related to EESSI. Today, I'm going to give a seminar about uh, CICD, and maybe even define what that means a little bit, at least in our context. And as I said already, if you want to ask me a question during the presentation or during, I have a pretty long demo as well. And so if you want to ask a question during either of those things, you're welcome to, right? Just speak up. Okay, so just to give a little bit of what would be helpful to your understanding of what I'm going to present today. And there was already two webinars in this series, and there was an introduction to EESSI, and there was also a webinar about building software on top of EESSI last week as well. And if you've seen those, that's probably going to be to your benefit today a little bit, and because I will be touching both of these topics again, and I won't be going into the kind of detail that you would have found in those webinars. So if you hopefully you've had a chance to see those, and if you hadn't, and if you're watching this after the fact on YouTube or wherever, maybe it's a good idea to check out the other webinars first before you dig into this one a little bit. And for those of you who are trying to follow this, or maybe trying to follow the demonstrations that I give as well, it is going to be helpful if you built the software package in some way in the past. Maybe that just means compiling something, but it would also be nice if you've heard of things like CMake and maybe even used things like CMake or Auto Tools or tools like that to build software. Also, I'll be using quite a few Git commands here, and also platforms like GitHub and GitLab as well. So if you're familiar with those, that will also help you a little bit to understand what it is I'm doing. I'll try and explain things as much as possible, but because I use these things every day, I'll probably gloss over details that might be important to some people. And the other thing I will be using is environment modules, and specifically LMOD, but you won't really know that, right? It'll just be environment modules. And so if you've used an HPC system before, it's likely that you've been exposed to these. But if you haven't, maybe they're new to you. On the slides afterwards, there's a link to a lesson that kind of explains what environment modules are and what are they used for. So this webinar series in general is built around the European Environment for Scientific Software Installations, EESSI, and what it enables, right? So today we're going to talk about the CI/CD part, but the core concept of EESSI is, what if you didn't have to install software? What if a broad range of scientific software was available on every system that you have access to, on your laptop, in an HPC cluster, in a cloud instances that you use, or basically any other computing platform where Linux can run? And what if that is possible, that you could use the same software in all those different systems without having to make a compromise on performance, right? So in some cases, people would say that this is already possible using various things. But typically there are asterisks involved there, which mean like the typical thing is that you compromise on performance, and EESSI endeavors not to do that. So the major goals are that this software stack that you have in all these different architectures and systems, that is uniform. It's the same everywhere, right? Exactly the same. That's one of the things that we try to, when it comes to the CPU, different CPUs, and we try to have exactly the same software in all those different environments. And we do that in a way where we don't sacrifice performance, right? So we want to give you the mobility of compute, but we don't want to force you to sacrifice performance to have that. And that is something that does happen with containers, because it's not easy to do this, right? It takes infrastructure to build for all these different CPUs and everything. And so not through any malice or anything like that, but just to make the workload feasible, containers and things like Conda, they typically take shortcuts here, and because it's just trying to manage the workload that's attached to making something like that functional. We want to avoid duplicate work. And this is it's a self-interest that really drives EESSI, because a lot of the people who are involved are making software available to researchers at different computing sites all across Europe. And so we want to avoid duplicate work. for the researchers, and so they don't have to set up environments and the different systems they have access to, for the support teams, for sysadmins. But like ultimately, this is work that we try and do also for ourselves, right? So we're trying to create something that's useful for all of these different groups and also for ourselves. So we don't have to duplicate the work we do on one system on all of the different systems that we might have access to across Europe. There are tools out there that help with automating the software installation process. And so the one that we use inside EESSI is Easy Build, and probably some of you have heard of SPAC as well. There are others as well. That there's a pretty long list, and Kenneth's given like a presentation on some of those that are out there already. But we would say that these are not really sufficient anymore, because you still have to, each of these tools has their own learning curve, and you still have to run the steps, right, to make the software available, right? So there's still a bit of effort involved in getting the software exposed in all the different systems, even when you have these tools available. And we want to go beyond that. We feel that the time is right and the technologies are there to allow us to do this, and that we can go beyond just sharing recipes, like the way to install software, but we can actually share the software itself, right? And that's what EESSI does. It doesn't share recipes, it's sharing the actual installations across all those infrastructures. So it means you're using the same binaries, and depending on the architectures, that for a specific architecture, it's exactly the same binary. And for a different architecture, it's a piece of software that's built in the same way and a very predictable path. What does this enable? This does lots of things, right? Apart from the fact that you have the same software everywhere, which means you can carry out your research on all these different locations using the same software stack and knowing that you can move your workflow easily between places. But it also facilitates things like HPC training. So it means you can construct a cluster in a cloud environment and be able to have a fully functional scientific software stack there in minutes, right? There are tools like the one that we use called Magic Castle that can bring up an entire cluster in about 20 minutes, including the entire software stack, right? Because it's being delivered through EESSI. And so you can have a fully functional environment that's equivalent to the environment that you have maybe on your compute systems. And then the other thing that we're going to focus on today is about the development of software. So because you have something that you can make available in cloud environments, this can really help the development of scientific software, right? Because you can have VMs or virtual machines that don't live very long, that are maybe used for a specific purpose. In our case, this is going to be continuous integration. But we can have a full scientific software stack in those environments without having to maintain it ourselves, right? Because yes, you could have a container in a software environment, or you can configure your own virtual machine, right? But you have to do all the work to maintain that environment, right? So that becomes a workload on you to make sure that whatever environment is in that container or in that virtual machine, that's up to date with your needs. What EESSI allows you to do is offload that part of the effort to somebody else, right? So we say, okay, I accept that the EESSI environment is useful for me, and I'll use it, I'll take it, and then I won't worry about the environment of the cloud infrastructure because that's not relevant to me anymore. I just use the EESSI environment. So how does EESSI actually do this? So there are different levels to EESSI, right? So you've got the host operating system, and then we say we have these three different levels, right? The file system layer, which is how we get the actual files to the users of EESSI. There's the compatibility layer and the software layer. So to talk about these individually, basically we sometimes say that the software is streamed in, and that's done by a tool called CERN VMFS. And it's basically the file system layer. It's the way we distribute, make the files available on each of these execution environments. And CVMFS is the one that streams in the software and basically does it when you try and access a file. So once you try and access a file, CERN VMFS decides, is it available on the system? Do I need to get it from somewhere else? But it does all that work. You didn't need to think about it anymore. To you, it's just a file system. I see files, I try and use them. Somehow magically they end up on my machine, right? So it's the same idea as a streaming platform, right? For like Netflix or music or whatever as well. And we build our software to be independent of the host operating system. And how do we do that? We use something called a compatibility layer. The technology in the compatibility layer is just Gen2 prefix. We basically just build an operating system in an unusual location, right? And as it happens, that unusual location is sitting in our file system layer, which means we can distribute that operating system everywhere. And what does that allow us to be? That basically we effectively have a parallel operating system to the one that you have wherever you land, right? And it's independent of that operating system. So that gives us containers without being contained, right? Because we're in a location on the file system and we're not contained in any way. We can still see all the devices. We can still see all the drivers on the host as well. We can do lots of things that are just that little bit harder if you're using a container runtime. In terms of the software layer, what we do there is where we do our optimization, right? So we have software that we care about the optimization of. That all goes into the software layer, where we do it for different specific CPU generations and maybe different GPU types as well. So for quite some time now, we have CUDA, we have NVIDIA GPU supported, but as of last week, we are now moving to support for AMD GPUs as well. And then we also have some initialization scripts that actually detect the hardware that you are on. Right? Whenever you try and access the system, it figures out, well, what CPU have you got here? What GPU do you have available? What software should I expose in the system? Or what paths should I expose in the system for the software that somebody needs? In terms of the user experience, today that user experience is to initialize things, you basically source a script. And that's the thing that's going away and doing the architecture detection and everything for where you are. It's just a bash script, or depending on the shell, there's different ones that you can use, and depending on what your preferred shell is. But you basically go and source a particular script. It will figure out from there what architecture you're on, and then it will expose the correct path for your architecture to you for use in environment modules. And from there, then you can use environment module commands. You can module load a certain GROMACS module, which might be a certain version built with a certain toolchain. And from there, you just start using it the way you normally would. So if you're familiar with GROMACS, you maybe have heard the GMX, and you can just start using the GMX binary. That's it. And you don't have to do anything else. What actually happens in the background is when you try and access a file, CERN VMFS talks to the local client cache, sees is that file already available on the system. If it's not, in the background, it will go away and talk to a mirror server and to pull that file information in. And then we have a central server. So there's lots of these different mirror servers around, but we have a central server that is the main copy of all our data. And these are all mirrored out to these mirror servers. So you typically talk to the local client cache. You might talk to a proxy in between. But basically all of this stuff, from you as a user, this is all hidden away. You don't see these things, but they're configured by sysadmins, right, for performance and everything. And yeah, the feeling for you as an end user is that this is on demand, right? Something is there. I maybe don't even notice that it's a little bit slow to arrive the first time, but when I try and use it the second time, it's already in the cache, right? So it's basically a local file system at that point. So the performance is really good. And it was designed for exactly this workload. It was designed to deliver software like this. So the performance of that, accessing those files, those kind of small files, is really good in this file system. But to get to the point of today, right? So that's the background of why it's a good tool for what we want to do today, which is continuous integration, because it means we can use it in an ephemeral way, right? We can create temporary resources that we want to use to do a particular job, and we can have a full environment in there that we can use because of how easy it works. So what is continuous integration? It's basically this practice of testing code, of frequently merging code into a shared repository. So what does that mean? It means I do a small development, right? I make a small change. I push that code into a platform like GitHub or GitLab. That triggers something, right? That triggers some work. So what you have then is an automated build and test for each of these code changes on that type of platform. And what does this allow us to do? It means that we can detect bugs early, and also that we can improve code quality, right? So if every little change is being tested along the way, it's very hard for a big problem to enter, right? Because we're testing at small contributions. It's very easy to see when a problem arises, where it arose, because the changes that are involved in that small push are small themselves, right? So we can locate things very quickly. The other thing is that it provides immediate feedback, right? So if I make a change, if I make a commit in a Git repository and then I push that commit, that gets tested straight away. If something goes right, I don't get a message, right? If something goes wrong, I immediately get a message saying this no longer works. Something is broken. And then exactly what you're testing will tell you what's broken, and maybe the code changes will tell you why that's broken, or you can figure that out for yourself. And what it also does is helps us to ensure that the application is always in a deployable state. So whatever we have, whatever we're showing people in the outside world in our Git repository, if we use CI, we can know that if they take a copy of that at some point in time, and it will build and it will work, right, to some extent, right, based on how good our testing has been, right? We know that that it should be deployable, that it should work for them. What are the key components then? So based on that, then what are the key components of this CI system? Well, we need version control, right? So, and these days that nearly always is Git, right? So we have a version control system like Git, and really Git's really powerful in general. It's used in lots of places, but the main reason that we would look at this today is because of the CI integration, right? Because of the powerful tools that you have, like these collaborative tools like GitHub and GitLab, where you can do all this code review and you can do CI and everything, and all these things can be integrated together. This is all, in terms of an ecosystem, it's very, very powerful for software development, right? And so this is built on the back of Git. So the one that we will look at is Git, and first that's our version control system. Then we have an automated build system, right? So we need some way to build our software automatically. That might be a shell script, but maybe other people use tools like Auto Tools or CMake or all of the other build tools that are out there, and there's lots of them. And you also want some automated testing. And so again, at the most basic thing, an automated testing might be a shell script, but there are also lots and lots of frameworks for you to use for testing as well, right? Depending on your language, depending on lots of different features that you might require. There's lots and lots of frameworks that you could be using for these types of things as well. It doesn't really matter what they are. It just matters that they exist and that you use something that's automated, right? So you want a way to be able to run a test and check that test point, right? And then that's basically it. And then you want the important part is that if something goes wrong, you want to know about it, right? So you want to be able to check the status of your CI, like did the last one pass? But if something goes wrong, you really want to know what happened. When you want to know immediately when that happened as well, and so you can go and check that problem. Right? So you want some kind of feedback mechanism as well. What are the benefits? So one of the big ones, of course, is that you see problems early. Right? So if there's an integration issue, if you see a problem, you'll see that early. You'll get notified. You'll be able to look at the problem and hopefully solve it really quickly. It also leads to faster and safer release cycles. So if you're constantly testing your code all the time, the chances that when it comes to a release that you're going to have some hidden code, some hidden problem in there, it's just that bit less likely, right? It's less likely that you're going to have problems in your code itself. It also encourages you to make small changes, right? So if you know every time I make a little change, I send it up and it'll be tested, and I don't have to worry about that. It just happens automatically. You're much more likely to make small changes, right? Because you know that if you make a big change, it's that much harder to find the problem, right? So it's easier for you to make small changes, push them up, and then get notified if there's a problem, right? But typically, if there's not a problem, then you get no information. You just keep doing your development, right? So it encourages you to make small changes and to push them up all the time, right? To have that CI doing that work for you in the background without you manually pressing the button on it. It also encourages improved code quality and team collaboration, right? So the fact that you can do this means that you can think a lot more about things like testing in general, right? So the quality of your CI depends a lot on the quality of your testing as well. So the testing becomes more important to you. I want my testing to be fast. I want it to be accurate, right? So you improve the quality of your testing. That also leads you to better code in general, and it facilitates things like team collaboration. So if you've ever been involved in a project where there's a pull request or a merge request, right? This team collaboration is where you look at each other's code, you make comments, you ask people to make changes, and they can make those changes. They can see if they fix problems or if they still build in the build system and everything. It just makes this kind of work, of this kind of teamwork, that much easier. And in the end, once you have all these things flowing, it makes it a lot easier for you to refactor your code as well. So once you have CI and once you have a good test suite for your code, you can trust yourself to refactor your code, right? You can trust yourself that you have something that's resilient in terms of testing, which means it's much easier to make changes there. You can say, okay, I can refactor this, and if my test pass, I know it still works, right? So I'm happy about that. So it makes refactoring and the code maintenance in general just that much easier because it's not just you who's going to maintain your code. Hopefully, in the end, there's a group of people, right? So we can all trust each other, right? So if we can trust the test suite that we have, it makes it that much easier for us to to allow people to make changes to parts of the code that maybe we personally are not familiar with, right? But we trust that the CI can cover problems there. And so maybe we don't have to be so familiar with pieces of the parts of the application, even when we're reviewing code for somebody else. There are specific challenges, though, in the HPC space, that are like an elephant in the room, but are really important to address for us, right? So, in the HPC space, you need suitable tool chains and dependencies, right? That in a lot of cases that means things that are really, really recent, right? So really cutting edge stuff, right? You need really recent compilers. You maybe need specific versions of compilers. You need dependencies, and they typically need to be very recent dependencies because maybe you're relying on targeting some very novel architectures, right? So you require the really bleeding edge versions of different dependencies and things like that. Um, you also need a way to deal with MPI. MPI exists in parallel systems. It's still the standard, right, in terms of communicating between processes. That's still the standard that's out there. And so you need a way to deal with that. You have to deal with the fact that this is required for you. And there's lots of developments that have been going on in the MPI space that are going to make this easier going forward. And it is already a bit easier now than it was in the past, right? Because there are ABIs for the big implementations like OpenAPI and MPitch, and there are ABIs there. There is an approved standard now, for the MPI ABI in general, and so things are definitely improving in this space. But the reality is that you, as an application developer, you need to deal with this. Then you also are typically interested in specific architectures. Right. I just don't just want to test for any architecture. I want to test for one of the supercomputers that I have access to. And that is, for example, an A64FX system. So it's not enough for me to test on x86. I need to test on an ARM system. But maybe not just any ARM system. I need to test specifically on an A64FX system because that's the one that matters the most to me. So these things that makes CI just that little bit harder. Right? And then we also want to have accelerator support. So we don't just care about CPUs. These days, especially in the HPC space, we care a lot about accelerators, right? We care a lot about GPUs and whether they come from NVIDIA or AMD or somewhere else, right? We want to know that our application is working in that space. And that basically means, again, we need access to hardware, right? So if we really want to test that, we need access to hardware to make sure that things are still working there. And even then, that's still not enough, right? Because another feature of what we have in the HPC space is that we care about performance, right? And we care about scalability. So it's not enough to test it's potentially not enough to test in a single node, right? We don't just want to know if things work on a single node. We want to know if they work across a network as well, right? So if we have multiple nodes at the same time, do I have problems there? Do I have scalability issues? Do I still have the performance I had in my last release when I run on 10 nodes? Like these are things that actually matter in the HPC space. What can we do to leverage EESSI? EESSI doesn't solve all of these problems, right? So the architecture stuff is still an issue. It allows you to address these problems in some way, but it's not going to give you a solution for everything, right? It can't pretend that just because you use EESSI, you have access to a GPU. You don't, right? But it does give you the infrastructure to allow you, if you do have access to the GPU, that you have a portable environment that you can use in that architecture. So how can you use EESSI in CI environments? We have two tools that you can use, right? So one of those is on GitHub. So we have a GitHub action. So the EESSI GitHub action is a URL here that you can also click on when you get the slides. And in GitLab, they have something similar that's relatively recent called components. And so we also have a component for GitLab as well. The nice thing about the GitLab one is that you can have that on GitLab.com, but you can also have that locally. If you have a GitLab instance that you maintain, and that's maybe connected to your institute or your university or something like that, it's still possible to use the EESSI GitLab component on that infrastructure as well, right? So that's quite powerful. what can EESSI actually provide you with? It can give you different compilers that you can use with your software, different versions of GCC. And now we have LLVM as well. And we also have RockM LLVM. So things are moving and we make more compilers available and more versions of the compilers as well. We can give you the dependencies that you require for your software. So whatever they might be, we have capabilities to add that to EESSI and make that available to you. There are also lots and lots of additional tools in there, right? Maybe things that you don't actually need today, but maybe you need them in the future. So some things we use ourselves, like FreeFrame for testing environment that we use for EESSI. But you also have performance analysis tools. You can have maybe optional dependencies. You can have lots of other software that's inside an EESSI because it's a full environment. There's essentially an unlimited potential there in terms of what you can add. There are things you might not want today, but you may want in the future. Other than CERN VMFS that you need to get access to EESSI, you do not need to install anything else, right? So it's a constantly moving environment. And once you install CVMFS, you don't need to do anything else. That environment is constantly being updated with new software, with new versions, with new compilers, with new dependencies. They're being added all the time. But you don't need to do anything additional to get access to new software. It's a maintained environment for you. Everything that you use is pulled in on demand by CERN VMFS. So of course, this means that because you have this consistent environment, it makes it a lot easier for you to run CI tests in lots of different contexts. So maybe you run it for free in GitHub, right? On the runners that they provide for free in GitHub. But maybe you also need your own custom environment as well. You can have the same environment, you can run the same code in all of these places as well. So the one thing that it was touched last week in a lot more detail, right? So I'm not going to go into it here, but just to mention that, so in the CI environment, we're not building on the host operating system, right? We're building on, if you want this portability, you need to build on top of what EESSI offers, right? That means building on top of the compatibility layer, reusing the dependencies that we offer and everything, especially if you want to be quick, right? And because you can install your own dependencies, but that's going to take time. If you want to be quick, you should reuse as much as possible from what EESSI is shipping. So to do that, you need to load the necessary modules that you need for your compilation. So that's your compiler, your MPI, any libraries that you need, any dependencies that you need. And you should try and pull as much as possible in from EESSI. It's more than a good idea to keep the dependencies in the same tool chain. So what do I mean by tool chain? It's I'm very, very used to saying the word, right? But from an EESSI build context, it has a specific meaning in EESSI build. But I think a lot of people are in general familiar with that. It means that you want to use the same compiler for everything. You want to make sure that the versions of libraries that you use is consistent across all your different dependencies. That is sometimes called dependency hell, right? So trying to ensure you have consistent environment across everything that you need. But EESSI hopefully will allow you to do that. The other thing that we use inside EESSI, at least today, is called a build env module. And this is useful for a couple of reasons. The first reason is that it sets environment variables for you that are commonly used, right? So why do I say commonly used? There's two big tools that use these environment variables. So that's that's auto tools and CMake, right? They listen to these environment variables. And because these tools listen to these environment variables, lots of other tools do too, right? Because there's a reasonable chance that they're going to be defined. So the build env module sets environment variables that typically influence the build tools. And it also sets compiler wrappers, right? So the compiler wrappers are basically, they're designed to help simplify building with EESSI, right? Because you have to ignore the host operating system and push through the compatibility libraries of EESSI, these compiler wrappers help you to do that. And with that, then, I want to start with a big, long demo of showing you how you can actually do this, right? So we're going to start from a package that I've been maintaining called CI/CD demo. And it just has two dependencies, two main dependencies. It requires HDA5 and it requires MPI. It builds with CMake, and then you can test it using the C-test tool that comes along with CMake as well. For those of you who are looking at this afterwards, there's on the slides will have this URL, which is a cheat sheet for all the various steps that I'm going to do as part of this demo right now. So with that, we'll go to the repository. Okay, so here we have this CI/CD demo. It's what's called in GitHub a template repository, right? So I can just use this template. It's basically going to make a copy of this repository for me that's not connected to the main repository. I'm going to pretend like I created this code myself. So it's going to create a new repository, and I'm going to call that. I've already done this, of course, right? Because I tested this already, but I'm going to call that CI/CD demo. And I could here include all the branches. I'm not going to do that. I'm just going to, for now, I'm just going to include the primary branch. And if I did click this button, it would include all the branches, including the solution branches, right? So if you wanted the solutions as well, you might click this button. But we won't do that for now. And so we'll just create this repository. And that should just take only a few seconds. Okay. So this is my new repository. Here I have my CMake list, and because I'm using CMake, these are the two pieces of code that I have. They're C++ code, and we're not going to look at what they actually do, but basically they're just creating some files using HDF5, and then you create them using MPI run, and then you can actually verify them as well, right, that they're written correctly as well with HDF5. And so this is the README here. And so it explains exactly what happens inside. It explains what the requirements are. They're very loose requirements, right? They just require a minimum version of CMake, and some MPI, whether it's OpenMPI or MPICH, don't care. And then we want HDF5 with C++ support, right? Because we have C++ code. It tells me how to build the package, tells me how to run it, and it tells me how to verify it. And then it tells me how to test it as well, right? So I have a test step down here. So we're going to do all of that now, right now, with EESSI, right? So let's take the code, and we're going to copy the URL, and then I'm going to open a terminal. Is that big enough for people? I think it's already reasonable size. If I don't see any complaint, if I don't hear a complaint, I'll assume it's a reasonable, okay size. So we want to do git clone on the Git repository that we just had. That's going to clone that locally. Let's go and take a look inside. It looks the same as what we just saw online on GitHub, right? No surprises there. Now, when we let's look at the README again from here, piece by piece. So we can see here, it's telling me how to build the package, right? But of course, first we need to load our dependencies. So we don't have EESSI available yet. We know that the way to do this is to use the source command, right? So this can be found in the EESSI documentation, right? Exactly, because I understand that it's a long path to try and remember it. Of course, I remember it, right? Because I use it all the time. But if you need it, then it's in our documentation about where to find that, right? So I'm going to source this command now. And then in my case, I had sourced it before, so it's already done a reset. And so you can't actually see the architecture I have, but I can show you. So we can see that it's selected. I have I can't remember what type CPU it is, but Neoverse N1 type CPU. So I have an ARM CPU on my laptop here. And that's what it's found for me, right? So now I have lots of software available, module avail. We can see lots and lots and lots and lots of packages, right, are available right now. But I'm only interested in a few. I want to load HDF5. And if I do that, I can do a module list. And I see now I have HDF5, and I actually already have OpenMPI as well, because HDF5 also requires MPI, right? So when I load HDF5, I also get all the dependencies of HDF5, which includes MPI, right? So now I have most of the things that I need. What I don't have is CMake, right? So I need to load CMake as well. So I can do module load CMake. Well, now that I picked a version of HDF5, I probably want to make sure that I'm picking a version of CMake that's compatible with that, right? So I can look at the environment that I got when I loaded HDF5, and I see things. These are the tool chains here, and I see that I've got GCC core, which is effectively like GCC. You can see GCC over here, 1430, right? And so I might as well take a version of, I should take a version of CMake that's consistent with that environment. So let's do that. So let's take this version of CMake. Now I have the dependencies that I needed to build my package. So let's go ahead and do that. So if we look at the, let's look at the README. It tells me what to do. It says, oh, make a build directory, go in there, use CMake, and then just build it. So I'm going to copy those build instructions, and I'm going to paste them here locally. So I'm going to run each of these commands now. So here we can go away. You can see it's detecting compilers that are sitting inside CBMFS, right? So it's already detecting our compilers. And it says it's found HDF5, so it found 1.14.6, which of course is consistent with what we saw when we loaded the HDF5 module. And it built my executables. Everything looks good, right? So I built my software. Seems like it worked, but there was something else I needed to do as well, right? So I need to also, I need to also test my software. So let's have a look at that README again, because it did tell me how to do that, right? So I've changed directory. So let's look at the README again. It told me how to build my software, and then it told me how to run my software, but I'm actually interested in the testing steps. So I want to also know, how do I test that software? So let's have a look at that. I copy that command again and paste it into my terminal, and it fails, right? So I've got a problem here. It didn't work. Why didn't it work? Let's go back up. Because I used the command I used with CMake, included verbose output. So I get output on the screen here that I can go back and check. I can see here's where I run my command. It says start to run the MPI program. And then it says error loading shared library. Error loading shared library, right? So I have a problem with loading my shared library. If I go back to the documentation on how to build, where is it? On how to build with EESSI, right? So we're looking building on top of EESSI. So where am I? I missed something, I think. Sorry, 1 second. Yeah. I actually don't have a link to the documentation here, right? But I should have a link to the documentation here. But if I read that documentation, it describes exactly this problem, right? And the problem is the linking part. The problem is building on top of EESSI. Where does the loader find the libraries, right? Why do we need this build end module? We need it because it creates wrappers that gives hints to the loader about where it should find the libraries. And so what is a dynamic? So there's a couple of different names that are commonly used for this thing. So basically what happens when you create an executable, and let me make this full screen. When you create an executable, when you create it that uses shared libraries, what happens is you have something called the runtime linker or the runtime loader or the dynamic linker, that loads the libraries that you need at runtime. Right? So how does it find those libraries? The nice thing about the runtime linker is that you can change its behavior at runtime. You can tell it to find it in a different place, right? So, but how does it actually do that then? So you can give it clues via environment variables. So the one that people have probably heard of before is LD library path. Or you can actually inject information into the executable itself about places where it can look. And so the one that we use is R path. There's also run path as well that can be inside the executable, and they have slightly different behavior. But basically, there can be information in the binary itself as well. And then the linker also has its own defaults, right? So it has its own places that it will look for the libraries as well. The reason that EESSI is like a different operating system is because EESSI ships with its own runtime linker. And when you compile an executable, you're compiling it against the linker that EESSI ships. Now, it still listens to the typical environment variables, but because we use RPath, a lot. So we resolve libraries using RPath for a lot of cases, but we also control the defaults where the linker looks, right? So that helps us in terms of when it comes to like resolving libraries for devices like your GPU, and this is very powerful for us. So that's what we use. And so basically we need to influence that behavior. The problem is, in our case, when I compiled our code, we no longer have enough information to be able to find the libraries that we need, right? Because we didn't use the RPath wrappers that are shipped with the build-env module, and we don't have the RPath information. So we don't have the location of our dependencies encoded inside of our binary, right? Inside of our executable. And so to be able to do that, we need to actually start again. And so let's remove what we have in the current directory. We need to also load another module. We need to load the build-env module so to get access to those wrappers. We need a specific version of that. The stuff that I'm using right now is the latest. That is not the latest that we have. That's 24. It should be 25. 25B. All right, that's one that's consistent with the environment that I have loaded at the moment. And so I'm going to load that module as well. And now I'm going to rerun my build step. Okay, so I've emptied out my build directory, and now I'm just going to rerun CMake. And if we look, the things that are interesting here is, let's look here, for example. So you see before, we found the compiler, right? Our C++ compiler. It was in a certain location, but now we see it's coming from a different location. It's coming from the build-env module, right? And there's a bit of a giveaway in the name here, explaining to you that you're using an RPath wrapper, using a wrapper around the TXX or the C++, right? Your C++ compiler. So CMake is now picking up, instead of picking up the C++ directly, G++ directly from the compiler installation, it's using our wrappers instead, right? But otherwise, things look the same, and we got the same version of GCC. We got the same version of GCC. We got the same version of HDF5 and everything. So things look good. We've also got the MPI as well, or that version of the ABI. So we can compile. We can compile. Right? We didn't have a problem compiling before. We don't have a problem compiling now. The step that we had a problem with was our C-test step, right? So let's run our C-test. Sorry, the queue there at the end. So let's run our C-test step again. And this time around, things just work, right? So we have something that compiles, right? So we were able to use our CPath wrappers. We no longer have this problem with finding the libraries that we need, right? So now we've got something that works, right? We're not here to just build on top of EESSI, right? What we want to do is reproduce that workflow in a continuous integration environment, right? So how do we do that? The first thing that we do is think about again, here, right? We had our different tools, right? So to start with, we're going to use the action, the EESSI action, and that has some setup for you. It tells you like how you need to do that, right? So the first one we're going to do is the EESSI action. So let's okay, so let's go to the EESSI action and see what does that look like, right? So if you clicked on that link, this is what you would see. You have some description about EESSI in general, your description about what you can do here. There's some examples as well. This is the first one, which is really minimal. It just says, oh, you need to check out. So this is a YAML-based workflow. So essentially, GitHub is interpreting this and taking certain actions based on what it finds inside. So the first of those is to actually check out the repository, right? So to check out your code and make it available. Here, we're telling it to use the GitHub action from EESSI, which is configuring all the EESSI environment for you to run. And then this example here is basically a script, and you're just saying this one has got just module available. It's just saying using module available. A critical thing here, and it's mentioned in the docs, is that you need to use the bash shell, right? So in GitHub Actions, you must use a bash shell because we use a trick, right, to make EESSI available and make it initialized already in the environment, we use a trick, and that trick only works, as far as I know, with Bash, right? But the second example that they give is a bit more than minimal. And it says you can run a multi-architecture workflow, so an x86 on ARM. So this is available to you for free on GitHub these days. So this is the syntax that you need to be able to run a multi-architecture workflow. So here before it said, you're running on the latest Ubuntu, right? That's what it said. The implication with this under the hood is that this is x86, right? So this is probably like, I think it's a Zen 3 system that's underneath it, but it depends. It changes from time to time what architecture you end up on. But that's the operating system that you have. You've got the Ubuntu latest, right? Here, you're making a specific choice. You're saying 2024-04, that specific version of Ubuntu, but you're given two options, and you can say you can run on this on both of these options, right? So this one is an x86, and no guesses, no prices for guessing here, but this one is an ARM basis, right? And the other steps is the same. There's an option included in here because it's saying you can choose the version of EESSI that you want to use. So in this case, the stack version is 2025-06, which is also the one that I want to use, right? So I'm going to use this option. So we can take all of this text and put it in a certain place, right? So you can use like documentation to figure out where that place would be. But in our case, for GitHub, right, the location that we want to create things in is in a certain directory called. So we make there -p. So we make a directory called, let's get out of the build directory first, go back to the root of the repository, right? We're going to make a directory called .github. Your CI has to be in a subdirectory called workflows in there. So we make enter -p. So we're going to, neither of these directories exist, so we're going to make them. And then we're going to edit a file in that workflow. We can call it whatever we want, but it is a YAML file, right? So we have to make the YAML extension, right? So we're going to call it build with, oops, no, that's not cool. Build with EESSI.YAML, okay? So we're going to create a file in here. I'm going to edit. I'm going to paste what I just had. And that looks okay to me. I don't know, let's say, because I haven't used CI before, but this is my first shot. So now we have edited a file, git status, right? We can see that we've added this new folder. Let's add it. So that's add this new GitHub folder. Let's do git status again. We can see we've got a new file in here that we want to add. Let's git commit that file with the comment, the remark, and add CI using EESSI, right? So we're going to commit that change. I didn't want to commit it to main. I actually wanted to commit it to a branch. So let me check out -b on a new branch called CI. And we can see that, use git log to see that we still have the one that I just created. So this commit is still in this branch. And then I want to push this new branch. This is my feature branch, let's say, where I'm adding CI. I want to push this new branch, git push to the origin CI. So we can see git remote -b will tell us what remotes we have. So the one we want to push to is git push origin and then our new branch CI. And I have the key already for the Git repository in my SSH agent. Again, I'm not going through into the details of these things now, right? But we pushed the information to here so we can go and take a look at what happened. So we copied that URL, we paste it in. It's saying, oh yeah, you want to open a pull request. Here's the information. It's the same text that I had in my commit. I can look at the changes that are made. Yes, this is the new file that I introduced. Let's try it out. So we create pull request, and then you expect something to happen, right? So I added an action. I added CI. I expected something to happen here, but nothing does. Why not? All right. So this part is a little bit tricky. If you don't know your way around these things, you wouldn't necessarily know where to look next. But you have a tab up here called Actions. And if we click on that tab, we can have a look and see actually there's something here that failed, right? Never even reported in the pull request, but something happened. and it failed, right? So we can go and click on that and see what happens. It says nothing can be shown here. It just says status failure, but there's a little piece of text down here, and that is a hint, right? So we have this annotations, and it says no event triggers defined on. Now I know what this means, but you don't necessarily. So let's take this text, and let me just hide. Let's take this text and use an LLM, right? Because LLMs know CI stuff pretty well. We can say, in my CI, I got this error, right? When I used, and then let's go back to our file, and let's cat our file.github. Let's cat this file. So this is the contents of my file. Let's give that to the LLM as well. Okay, it's chewing on that, and it goes, here you go. Your workflow is missing the top, and it explains everything, right, about what's wrong with what I've done, right? And it tells me how to fix it. And to be honest, tools like these are very useful for CI. So if you have problems with your CI workflow, give it to an LLM and see how far you can get with getting help, right? Because in my case, I'm missing all this text apart. So what does it mean? It explains in the text. The LLM will explain, and if it doesn't explain, you can ask more questions. But basically here, I was missing a trigger. I didn't tell it when to do the CI. I haven't told it on what kind of events, like on what scenarios should it actually run this CI, and I need to give it that information. So what it's telling me to add is to say, in this case, it's very broad. It's saying any pushes. So anytime I push up to the repository, run the CI. Anytime a pull request is created, run the CI, right? So this is very broad right now. You might want to limit this, but we're going to take that. We're going to do exactly what it said here, and we're going to add that, right? So let's go back and edit our file again. Let's add this back. So we can add this, and let's change this name. It's a bit build in using easy CI. Let's give something a little bit more descriptive here about what it does. And this one down here, this name down here is also actually, this is just doing a module avail, right? So the problem is here, this is not actually building my package at all yet. We'll get to that, back to that in a minute. All it's doing is a module avail. Let's just see if it works first, right? So git add, and this updated workflow, commit minus m, add CI trigger, git push origin, and our CI branch, right? So let's push that back. Okay, let's have a look and see. This keeps coming. All right, let's have a look at our pull request. Now we see there's this little dot here that wasn't here before, right? So if we click on the pull request, we can see something has happened. Now we have all these little spinning circles here, right? So something has now happened with our workflow. Let's go and take a look. We can see it's actually going through these steps that we saw, right? So it's to set up the job. It's a separate thing that GitHub does, but it's running this thing. Oops, let's close that for a second. It's running the checkout, so it's checking out code. It's running the easy GitHub action. Takes, I think, about like 40 to 60 seconds, right, for this. So to get the entire software catalog that's available with Easy, you have that in your CI environment in under a minute. The first time around, it creates a cache. So the second time around, it's even faster, right? But I expect that this should be available under a minute. And sometimes on a specific architecture, it might be that much slower. Let's have a look. Yeah, it's a minute here, but it should be available. Yeah, this one is already done. Right, so this one took 59 seconds. And the test that it has for Easy right now is just the module avail. And you can see it's a big, long list of all the software that's available inside Easy. So all of this software is available in my CI environment already. And great, but it's not useful for me, right? Because that's not what I wanted to do, right? I wanted to make my software available in Easy. So I want to change the workflow to suit what I want to do. So, oops. So let's go back to VI here, right? So we don't actually want to test EESSI. We want to build our package with EESSI, right? So we want to build our package with EESSI instead. How do we do that? It's exactly the same steps that we had previously, right? So first thing we want to do is we want to load the software that we're interested, load the modules that we're interested in, right? So we want a module load HDF5. We know that brings OpenMPI as well, so we don't need OpenMPI as well. And we also want CMake, and we can take the latest version. That will be a matching one. In general, you should be quite specific in what you want here, but I'm being general, right, to save myself keystrokes right now. And then you also want build-env as well, right? So we want that build-env. What do we do next? We make their build, we cd into build, we cmake dot dot, and then we make. You can use -J to build multi-core, just to speed it up that little bit. And then the last thing we want to do is that C-test step. Now, I don't remember the text for the C-test. Oops. I don't remember the text for the C-test. Let's go back and let's look at that again. So that's the full command. We just take it from there, just as we ran it in our terminal. Right? We go. Let's go in here and insert that. Right, so that's finally our test step as well. Right, so we take all that. Looks okay. Let's add that. All right, let's add that. Let's commit the change. -N. Actually, build and test. We want to push that change. Git push to our origin again, CI. And let's have a look, see what's happening here. Right, so go back to our pull request. And we can see all the different things that happened. We had our first commit here. Nothing happened because we didn't have a trigger for our CI. When we added this trigger, we got something that worked, but it wasn't actually doing anything that was relevant to our project. So instead, we wanted to actually build and test our stuff. That seems to be running now. You can see it's running 4 jobs. It's running the pull request trigger, and it's running the push trigger for the 2 different architectures, right? So that's probably a bit excessive. We could probably tidy that up a little bit. But for now, we're not going to do that. We can take a look at these. We can see we're only 30 seconds in, right? So EESSI is still being configured in the runner. This one is on 36. So that's still working. Yeah, we're still 45 seconds here. There we go. It's starting to build our package, right? So after 45 seconds now, we now have a fully functional environment. It's loading the EESSI module. It's loading all the packages that we need. It's told me that it's actually an Zen3 system and that there's no accelerators on here. So there's no surprises here, but there's no GPUs, free GPUs. It's loading the compiler that we saw before. We can see that compiler is coming from our path wrapper, so from build-env, just as we did in our own environment. It's building, it's linking, and it's going so fast that I can't keep up, but it's already tested things, right? So 100% test pass, 0 failures. We now have working CI for our project, right? So you can see the others are catching up right now. So we have 1 success, the others are running. Now we have 3 successes, in a second it'll be 4 successes, right? So we have working CI for our project already, right? And that's the core of what I wanted to cover today. But I want to give you a little bit more information as well. So I have a half an hour, so I think I'll have enough time to cover it. I wanted to also cover doing a recipe with EasyBuild. I'm not going to show you how to construct that recipe. I'm going to show you the end result, right? So first I want to make a directory EasyBuild. And then inside that directory, I want to create a new file which I call cicd demo.eb. And I'm going to use my own cheat sheet here, right, to give me the recipe and the recipe for this package using EasyBuild. And I'll just walk you through it, right, just a little bit. right? So in easy build, like I say, I haven't covered all this, and it is in the easy build documentation, and we've given tutorials on this in the past. So if you look around what we've done in the past, you'd be able to get some assistance on what these things mean if you're not familiar. But we use an easy block, a CMake easy block. So that's basically for easy build, it's just telling it some information about how do I build this package. And this is a CMake based package. So easy build is very aware of that type of tool. We give it a name. We give it a version. In this case, it's development version, right? Because I want to build a certain commit of the project, which is maybe the current commit of the project. And my project doesn't have a homepage right now. I could have maybe given the GitHub repository here as the homepage, but it doesn't have one. It's just a simple project that writes files in parallel. And the tool chain that I want to use is this one that we've seen, right? This Gompi based tool chain. I no longer need build-env because EasyBuild does these RPath wrappers itself. So I don't need that dependency anymore. So I can just use this GOMPI tool chain. Here I need to make a little change because the default is, it doesn't have a default basically because I'm using a template repository. So I need to put my GitHub account, which is what we see on the screen, OCAISA. The source URL looks like this. You don't need to touch it. It uses something called a software commit. I'll show you how you set that software commit in a second. And then we need the dependencies, right? To build it, I need CMake, right? But I don't need that at runtime, so that's called a build dependency, right? So when I'm actually running the software, I no longer need CMake, but I do need HDF5, right? To actually run the software, I need to link against those HDF5 libraries, right? So I need to build it with HDF5 as a runtime dependency. I also want to test the software, so there's a bit involved in figuring out how to enable this kind of testing in EasyBuild. But this is what in this particular case, this is what you end up with. You just have to say run test equals true, and it will run a ctest command with some options as well. It also has some sanity checks as well, so you can check and make sure that certain files are in place. You can also have sanity check commands as well to make sure that certain things run. And so that's basically it. That's the easy build recipe. How do I build that recipe? The way to build that recipe is to load a certain module. So this was covered last week to load easy extend. So to load the easy extend module. And then that sets up a certain easy build configuration, right? So I'm not going to do it locally on my machine here. I'm going to do it directly in CI, right? So we're going to make a copy of the .github workflow, and then we're going to copy that over to another workflow, which we call GitHub workflows, build with easy, and we're going to say easy extend, right? So we're going to copy that over here. Let's edit that file, GitHub, easy extend. So we're going to build with easy. Let's change the name here so make it easy. Oh, sorry. Insert dash easy extend. Okay, so we're going to change that. We obviously have to change the workflow that we're going to run. So it's going to be a slightly different workflow again. So we don't need this command anymore. We don't need to load build-env, but we do need to load the easy extend module, right? That was the one that we need. And then we don't need this anymore because easy build is the thing that will build. We don't need the tests anymore. So what do we actually run now? We run an easy build command. So it's EB. And let me copy and paste it, right? So I don't make any mistakes here. I'm going to do this. Right, so there's two things here that we really need. So one is the software commit. And that's basically a GitHub SHA that comes from, in our case, we want it to come from GitHub, but it could be any commit in the history of the project. In our case, we want the commit of the commit of the pull request that we're running right now, right? That's relevant to this workflow. And how do I find this environment variable? Like, just ask the question to an LLM, I would suggest, is the quickest way to get an answer here, right? So say I want to use a certain commit from the current pull request. How do I do that? It will tell you that the environment variable that you need to use is this environment variable, right? And then we need to give the path to the easy config. So in this case, it's under an easy build. This is relative to the root of the software repository. So in this case, it's for us, it's under this EasyBuild subdirectory. Right, we can do that. And then we can add this workflow. Git status. Yeah. Oh, I forgot to add the EasyBuild directory. I was wondering. Forgot to add this file. We need to add that one too. Git commit -m. Add an easy config with related CI. Okay. And then we can push this one up to our origin as well. Let's take a look at that. How's it going? We can see we have a new commit here that we just committed, and that's kicking off more workflows. We can see there's lots more of them now. There's double, right? Because we have 2 workflows. Each of them has 4 jobs. So lots of things have started now. These are all going to pass because we didn't make any changes to our software itself, right? So we're not, this is the stuff that's new. So again, this is configuring. The first thing it does is have to make easy available on the platform. That should be done in like 45 seconds or so. So let's have a look. And this one is still running. Yeah, it's coming. Now this one is already starting our build, right? So it just took just 40 seconds, right, to configure our environment, and then it's running these steps: load, easy, extend, and then try to build the software package. So let's see if this actually works for us now. Hopefully we'll start spitting some information soon. Yeah, here we go. Again, it's told us, oh, this time it's given us a different platform, right? So before we saw Zen 3, now we're on an Ice Lake system, right? So that's not a surprise. It does happen that we can have a different system. This is the beauty of EESSI, of course. You have the same environment everywhere, right? So even though I landed on a different platform, I'm still going to get the same software modules and everything. I don't have to worry about that anymore. And we still obviously don't have an accelerator. But then it's going through the EasyBuild process, right? So starting to process the easy config, telling it where it's doing things, it's walking you through what it's actually doing, where is it finding the sources, for example, right? Not this one, somewhere around here. So it's finding our sources. It's running EasyBuild hooks, it's loading the dependencies. Now it's running the CMake command, right? So it's actually running CMake with lots of different options, building that software. It's already run the test step. It was too fast for us, right? So it ran the test step already. It's installing the package. Everything is done. We got a completed success, right? So the 2 of them are finished already, right? So now we have another piece of CI that's building our recipe and using EasyBuild as well, right? So now we've done 2 pieces of CI, right? I think I still have time, so I'd also like to show you what this looks like for GitLab as well. So in the GitLab case, let's go back. I want to get rid of this. Yeah. So in the GitLab case, this is if you follow the link, this is where you end up, right? So this is actually, let me go back to if you follow the link, you'd end up here. So this is what you would see. You would see GitLab EESSI. You see a certain version. It tells you as well what inputs you can give to that version. The README is pretty important here again. You just want to read the README and see how do I use this, right? So these things are no surprise. You can use module load. You can do the things that you normally do. It's exactly the same as you would do in your shell. It tells you to use it in your own repository. You just need to do to give this syntax. Again, it's YAML syntax, right? So, and then to use a specific, it's the same as before. You can create a script, right, running certain commands. There's an example down here, and this is the one that we're going to use. So this minimal example is here. So it looks different to GitHub, that's for sure. But it's not that different in the sense that you just need to figure out, right, how do I get the version of EESSI that I want available? And this is the part that I need, right? And then how do I do the testing? This is where I get to the point where I run a script, right? So I only want to change what happens here in the script part of things. Okay, so I'm going to take all this text. Again, I need to create a file in a specific location, right? And this one is called .gitlab -ci.yaml. So this is the location that GitLab listens to. I'm going to insert my text in here, and we want to use the same syntax that because it's a YAML file, we can use the same syntax that we used for GitHub, sorry. So we can even take the same, like in here, we have the same environment as EESSI, right? So we can use exactly the same steps because it is the same environment. We don't have to do anything different, right? So let's just have a look again at GitHub or workflows, build it easy _easy extend. So here is the things that we actually have to run, just these two at the end, right? So let's take those two and stick them into our new GitLab CI. Okay, so we copy them, we paste them over. Indentation's a bit off, we'll fix that. Now, one more. Yeah. Okay. So this time we're using the EESSI GitLab component. That's just setting up easy for us. We just need to know how do we get to this point where we can use that environment and run our tests again, right? So in this case, I'm going to use the EESSI config and the EESSI config build step, right? So we have this. We want to add this new file, git commit -m, add GitLab CI. If I push this to the origin, is it any use? Let's do it anyway. But it's not going to be of any use to me because that's just pushing the code to GitLab or to GitHub, sorry. And that has nothing to do with GitLab, right? So I need to push my code to GitLab because that's where I expect to run CI. So I'm basically going to create a mirror repository, right? So let's create a mirror repository. I already created an empty repository to host this code, but basically it's empty right now. So it even tells me how to set up this empty repository. I'm just going to take, this is called a remote. I'm going to add a new remote. And so I'm going to add git remote, a remote, add, let's call it GitLab. And then that's the location of my repository, right? So my empty repository. And if I do git remote -v, now we see that I have a new location, right? So I have my origin and now I have this GitLab repository as well, right? So let me just take a look at my GitLab code for a second because I realize already that I have a problem here. I took a direct copy paste, right? But this is not, this is obviously this environment variable GitHub SHA is specific to GitHub. It's not going to work on GitLab. Again, this is the place where you would go to, like, where you would go to an LLM, perhaps, or the documentation, right, or Google or whatever, to figure out what's the equivalent in GitLab. And the equivalent in GitLab is pretty close, but different, right? So it's CI _commit _SHA, right? So I already know I have a problem there, and I fixed it. Come on. Okay, so I need to add that. I need to commit that change. Make sure. Use the GitLab commit ID. Okay, let's push this change to, we'll push it to both places. So we'll push it to our origin. And we're also going to push this branch to GitLab, right? So we're going to push this branch to GitLab. Now let's take a look at GitLab. And if I reload the page, you'll see magic happens, right? So we have all the things here. We have the same files, the same structure. It's the same content as the GitHub repository, right? Just in a different location. But we already have something running here, right? So this is our CI in GitLab. It's already running for us. The first thing it does is configure EESSI, and that typically takes not very long. It's just setting up a file. There's all the information about how to configure EESSI. Yeah, that's done. Takes a few seconds. And then in this environment, then we see that this part is passed. The next part is the build step. So let's just go back and go from here. So if we click on this CI button here, we can see that the configure step is run. Now it's running the build step. This takes a little bit more time, and you don't have as much like free CI in GitHub. There's a lot available to you. You have multiple architectures. You can run a lot of CI that's at no cost for you. If you have a public repository, it's at no cost to you. In GitLab, the amount that's available to you for free is more limited, but it does exist and you can use it. And also, it's a bit more likely that you perhaps might have access to a private GitLab instance where you might have access to more, they're called runners, right? So more resources to run CI jobs in a private GitLab repository, but these will still work. So it's taking a bit of time for this job to start up, but there we go. We can already see, right? It's already down to the module load easy extend part. So let's see what environment is picked up for us. And this is also a Zen 3 environment as well in GitLab. So we don't get to choose here. We just ended up somewhere on some environment, and that's working. It's now starting to run the build step. Looks a bit similar to what we've seen before. It's pulling down the sources, unpacking those sources right now, running. Yeah, it's good doing the configure step. So we should see the CMake command appearing in a second. Yeah, we'll take it to conclusion here because we're going to get there in the end. It doesn't take very long to build this particular project. Obviously, in your case, it might take, if you have a larger software project, it might take longer to build. But in our case, we can see, yeah, the build, it already did the configuration step. That took 20 seconds for the configuration step. The build step only took 6. And we had a test step as well. That's probably even further up now, but we can see we already had success, right? So now we have CI working both in GitHub and GitLab. Right? So we've done quite a bit in whatever, half an hour or an hour. And then so that's basically showing you how it can run. Obviously, I ran through that really quickly, right? And so there is an opportunity for you. If you have that cheat sheet page, you can go through this yourself, step by step. You can use that template repository and everything. But I just wanted to take you to the end and talk a little bit about some other things, right? So a little bit more presentation. Okay. So I just wanted to show you briefly that you can use EESSI with SPAC as well, and that also can be used in CI. It's still very early days for this, but we do have like a proof of principle in place, right? So there is some integration work with SPAC going on already. So maybe some of you have heard of SPAC, or maybe you're a SPAC user already, but this is possible. And so there's a repository that Laura has created that's where this integration work is currently ongoing. And it demonstrates that in principle, this integration can work. And the other day, I created multi-architecture CI, so similar to what we've just seen, but for something that's using SPAC, but using the dependencies that come from EESSI. And so I think I have that already open here somewhere. Let me see. This one, yeah, Spood, right? So this is the Spood repository and my fork of the Spood repository. I created a pull request against myself. And this probably looks a bit familiar. It's not that different to what I just showed you. The basic structure is the same up here. The steps are different, right? Because the steps are following the documentation that Loris has in his repository. I made one small change here because I want to make sure that I'm using things for the architecture. That's a bit bigger. I want to make sure that I'm using things for the architecture that I have. So I changed things around a little bit, but that's the only change that I made. And in the end, we can see, just as I did for my own thing, I have this little tick here that tells me that the different architectures run for both the push and the pull request. I can go take a look at them, look at the details of that output. Right, this I'm not interested in, that just set things up. But this is the build and test step. I can see it did some stuff, right? It's telling me about that it set up the demo, and these are the software that it found. It basically does some discovery to see what's available in the compat layer and things. So this is all the things that it finds in the compat layer. And then it also is aware of the different of some of the software as well to allow it to build. In the end, this one is going to build Quantum Espresso. So we got a spec that it concretizes. Again, I'm not that familiar with SPAC. I know a little bit, but not too much. But it's basically taking a spec from SPAC, it's concretizing that using the software that's coming from EESSI, and then it's going to install that. This one is without MPI, right? So it's just a simple case. But just to show you that it works in principle, you can see it goes through all the different phases, similar to what EasyBuild does, right? So it's running the CMake command, it's building it, it's installing it, it's available, and that was, it verifies. So, Loris's thing also verifies it just to make sure that the software comes from where I expect it to come from, right? That we're getting our dependencies from CVMFS, and then the installation itself is available here. And that works, right? So in principle, we have something that works here. So it's just to say that this is possible as well. So you can use other build tools if you can figure out how to tell them to take their dependencies from EESSI. And you can reuse this tool as well in other types of environments. The last thing I wanted to mention was continuous delivery. So we talked a lot about CI, but the title of the talk is about CI/CD, right? So we talked about continuous integration, but not about continuous delivery, not about like how do you deliver the software to your end users. We have maybe a take, I would say, on what continuous delivery means, because we're really thinking about production level software and maybe release candidates as well, right? So we're considering the case of those type of things, right? Release candidates for your software and the production releases of your software. Like, how do you deliver them to people? So EESSI is obviously a mechanism to deliver that software, right? For your production software, for your production releases, EESSI is a way that you can get that into the hands of your users. And for CD, for continuous delivery, we think more about thinking more about the release candidates. You want developers to commit code that triggers CI, right? If the test passed, then you want that code to be included in the release candidate. Once you get close to considering and releasing that software, your release candidate, you need to test it more, right? So it's not enough just to run CI, but maybe you have additional tests like regression tests and scalability tests and performance tests, right, that you need to run in your software before you release it to your users, right? So the release candidate is deployed to a staging environment. And then there's some kind of process that takes place then. Maybe that process is manual just because that's what that's all you can do, right? If you need to run a job that requires 10 nodes, maybe today you may have no choice but to do that manually. Right? So maybe there's a manual step here. Ideally, it's an automated process, right? That you just trigger a workflow that does all the tests that you require and reports back on how that went. And once all those tests pass, then it gets promoted to production, right? Whether that's manually or with some kind of control deployment again. Again, maybe you need to trigger that yourself, but somehow a release candidate becomes production through some kind of workflow. What can EESSI do for CD? Well, like I said, the production quality software can go to software.easy.io. It can go to our production environment. But we also are working on a development service called dev.easy.io. That is intended for release candidates, right? So the idea is that we have a similar distribution method, but maybe with a limited set of hardware, right? Supported hardware. We want to give more control to the developers about what goes into the repository for their software tool. And then we give them access or deployment to specific architecture. So maybe not the full spectrum, but the ones that they really care about, right? The ones that maybe make the most sense. Things like vector instructions on ARM systems, you want to be testing against that. Or maybe you want access to NVIDIA GPUs or AMD GPUs. These things can be supported in the development environment, right? To allow people to do testing of their release candidates in that kind of environment. Also, what we're working on as well is an EC test suite. The idea being that you can have a test suite where we can run a test suite on the different Euro HPC systems, right? So you deploy your package into dev.easy.io. That's potentially automatically picked up by our test suite, automatically tested across the Euro HPC systems. The information is gathered and then reported back through like a dashboard or something for your package, right? Just to give you back information about how things run. So this could be used to allow developers to access all these Euro HPC sites without the need for them to have direct access to resources on the systems. Because typically it's quite the workflow for people to have to apply for a project, get a project, and then deploy their software in that environment, run that software, gather the information, and then somehow collect that information for themselves and the other developers, right? So that can be quite a manual workflow, and we think we can help with that. But I think that's basically all I wanted to cover. If you want to repeat this demo for yourself, you can do that. Just go to that repository, use the template, make your own repository, and then you can test things out exactly just as I did. The cheat sheet hopefully is going to be very useful in that case. And it also has links back to all the documentation that you need for these things. And if we miss something, we can add it back later. Remember the different steps, right? First, try to build it locally, which means you need to have EESSI available. That was covered in the first webinar about how you make EESSI available. If you don't want, you can have it on your laptop like I just did. And if you don't want to do that, you can use Aptainer. And there's lots of information there about how you can make EESSI available. And transfer your builds to GitHub or GitLab or wherever you want to use. You can potentially port it to EasyBuild. The reason I plug this, the reason I plug this a little bit is because this is effectively an investment that you make for EESSI, right? So if you want to get your software into EESSI, in the end, you will require an EESSI config for that, right? So a recipe for EasyBuild to allow you to do that, right? So building up that recipe is an investment that you make for the point where you want to include things. So if you want to use our development repository or you want to use our production repository for your application, we're going to need that recipe. The best person to develop that recipe is the people who know the software the best, right? So once you can work together with us to help you get to a recipe that makes sense for your package. But then once we have that, the best person to know the requirements of your package and how it should be built and everything is the person who develops the package. So ideally, what we want to do is not take over, but actually work with developers to make sure that the recipes that we ship, which means the software that we ship in the end, is the best that it can be, given the restrictions that we have, right? And with that, I think that's it. And that's all the information about the links you can do to communicate with EESSI and everything like that. Most of this work has been funded recently by the project Multi-Scale as well. So these are all the partners that are involved in Multi-Scale and all the links for Multi-Scale project as well. Thanks a lot. So maybe open the floor for questions now.
Okay, thank you very much, Alan. If anyone has questions here and is happy to be asking those yourself while we're still recording, please raise your hand here in Zoom. Or just post a message preferably in the EESSI Slack channel or here in the Zoom chat if you don't want to speak up. There was a short question already in the EESSI Slack. So somebody suggested that you should be gluing commands together with a double ampersand to make sure that it only goes as far until it fails. But in the workflow, I don't think you typically need to do that. The workflow will stop automatically as soon as one of the commands fails, right?
Yeah, workflow. That's what it's for, right? So it's meant to catch failures, right? So every command is evaluated, and I mean the way it's set up is that if a command fails, it will immediately stop.
Yep. Yeah. I assume that's the same in GitHub as it is in GitLab, right? That's the whole point of these workflows.
I haven't tested it, but I would suspect yes.
Yeah. There was another question from somebody at BSc. So does the streaming mean that EESSI is not really effective on compute nodes without internet access? I suspect that's related to Mare Nostrum, but they didn't confirm that. And we already gave an answer. I mean, even for offline systems, there's a bunch of ways that you can still have access to EESSI as long as you have proxy servers or a mirror server inside of your network. That's really a non-issue. On Mare Nostrum, EESSI is already available system-wide, actually, and we've shared a link to the documentation of the Euro HPC Federation platform that gives more details on that. And Stammen here confirms it's indeed about Mare Nostrum. So there it's really a non-issue. I mean, EESSI is already available on Mare Nostrum. At least the production repository is software.easy.io. I don't think the dev.easy.io is there now, Alan, right?
I don't think so. I don't think so.
No. But I guess we could talk to the sysadmin team there at Mare Nostrum if that's also of interest. So Stammen, if you're interested in that, let us know, and we can see if we can make that happen. Okay. Other than that, I don't see any questions being raised. So this was a long demo, and I'm sure some people will be diving in. So we've shared the HackMD link in here in Zoom and in the EESSI Slack channel already. So if people want to get their hands dirty and test this themselves, they definitely can.
There's maybe one thing I should mention, and I kind of glossed over it. And what happens if the easy config, if the easy build goes wrong, right? So the difficult thing is getting back information out of the CI, right? So you can see the text output, but that's all you got, right? Unless you do something else, right? So there's a couple of options that you could give to EasyBuild. So one of them for EasyBuild is that you can log to the screen, right? So you can do all the logging to the screen. By default, in Easy Extend, it does debug logging, which is extremely verbose, right? So it means a lot of text would be printed if you log to the screen. So in the cheat sheet, I add two things. I onset that debug logging, and then I log to the screen, right, for the build. And then you can see, so if something fails, you can see what failed, what command failed exactly, and probably, hopefully, why that command failed as well. Right? So these are somehow interesting as well. So maybe that's one of the challenges. Is it's great when things work and because everything's all green, but when it doesn't work, sometimes if you need more information, you don't have direct access to the machine, right? So it's that much harder to get something out. You need to figure out how to do that.
Yes, okay, yeah, that's definitely useful to mention. Okay, it looks like we're not getting any questions in, Alan, so I think we can wrap it up here. Thank you very much. And a lot of this is also covered in the EESSI documentation, right? Both on how to use it in GitHub, GitLab. So people can also go and check there. If you do have any questions afterwards when doing this hands-on, don't hesitate to jump into the webinar channel and ask around. You'll definitely bump into someone there who can help, or at least try to help you if you have any questions. Thanks again, Alan. We'll wrap up the recording here.
Yeah, we'll just give a window for people if they want to have any other questions after this.
Some informal Q&A. Yeah.